Okay, so last time we discussed the concept of temporal coherence and the essential mathematical ideas associated with them. So we discussed Wiener-Khinchin theorem, the generalized Wiener-Khinchin theorem. We introduced the notion of cross correlation function and cross spectral density function. So today we will use those concepts to actually calculate the intensity at the output of an interferometer, and we will see how we actually calculate the correlation between fields in a real optical setting. Okay, so basically today's discussion will still be a continuation of second order coherence theory, probably the last lecture on temporal coherence. Next time we will start discussing spatial coherence. So this is a source. Let us say this is the field produced by the source. So let us pick 2 points, and here let us say the field is V of R2 T2. Here the field is V of R1 T1. So we want to find out, when we make a measurement here, we want to really find out what is the correlation between the fields at R1 T1 and R2 T2. So the generic question is, correlation So this is the question that we really want to answer. So whenever you study correlations or coherence, these are the kinds of questions that we will try to address. So basically you have a source and we want to find out what is the correlation between the fields at these two space-time points, R1 T1 and R2 T2. So what is the methodology? So what is the prescription to address this question? So let us now briefly sketch the methodology involved in this process. The first point is, of course, we need to consider the fields from these 2 points. Let us call this point A, point B. Second, we need to introduce a phase shift, a phase difference between the 2 fields. Why do we want to introduce this phase difference? We need this phase difference to observe interference. And third, superpose the two fields at some other point RT. Now this, the third point will be familiar to you because this is very similar to what you would have seen in Young's double slit experiment. You basically take the fields from two slits and you measure them at different points on the screen. So basically we take the two fields and superpose them at some other point RT. The fourth, study the correlation function by studying the intensity I of RT as a function of the phase difference phi. So the fourth point again tells us that what we will be attempting to do is to somehow relate the intensity at this point C to the correlation function V conjugate R1 T1 times V of R2 T2. Okay, so basically we will try to get all the information or try to investigate the correlation by looking at the intensity. Correct? Is this clear? So any question? So when we study temporal coherence, we generally ignore the spatial variation of the field. So we will only be concerned about the time arguments T1 and T2. So as we proceed with the analysis, we will, for brevity of notation, we will suppress the spatial coordinates, because we are not interested in how the field varies spatially. So we are only interested in the relationship between points in the wave at different times by analyzing how a point in one wavefront correlates with itself in a delayed wavefront. So basically we just want to study the correlation in time. Okay, so the conditions under which we study temporal correlations, we will ignore spatial variations. So now we will try to explicitly calculate the intensity by constructing an interferometer. So this is a beam splitter, this one is a mirror. This is a detector. So let us say that the field so this is the field from the source at points some point r naught and time t prime. So we basically want to measure the field at the detector at the space-time point rt. Now, so the field from the source hits this beam splitter and it gets split into two paths. Okay, so let us say that it takes time t1 for the field to reach the detector along this path, and time t2 to reach the detector along the second path. Okay. Now let us introduce a phase shift here. Now how is the phase shift actually introduced in the lab? The way we do it is by changing the path length of this particular arm of the interferometer. So how do we do that? Let me just draw that one here. This is the source. So this is again a beam splitter. This is a beam splitter. Right. So we introduce multiple mirrors to change the path length of one of the arms of the interferometer. So the difference in the path length, so the length of this particular arm is different from the length of this particular arm. So the difference in the path in the path length is what introduces a phase shift. So basically this dotted box with this label phi is a symbolic representation of this particular setup, right? So this is how we actually introduce a phase shift in the interferometer. So V of R naught T prime is the field at and T prime. So T2 minus T1 is the delay. We call the difference tau, right? So the question that we ask is, what is the correlation or in more physical terms, what do we mean by what kind of correlation are we talking about? We are talking about the correlation of the field vibrations at points A and B. I mean the field vibrations basically what is how the field that takes that travels through this particular path. Let us call this path 1 and let us call this path 2, right? So how are these two fields correlated? Okay, that's a question that we want to ask. So note that we are not changing the spatial coordinate. So it is still the field that is produced at this point or not. Okay, so we are not changing the spatial coordinate of the field. So R is the location of the detector. So R is the coordinate at which the detector is located. So V of RT, okay. So of course there will be an output here, there will also be an output here, but for our discussion we are only going to consider the output that is measured by this detector, because it really doesn't matter which detector, which output port you use for measurement. Okay. So what reaches the detector will be a superposition of the field that travels through path 1 and the field that travels through path 2, right? So basically that is nothing but K1 V of R0 T minus T1 T minus T2. So K1 and K2 are some constants. Okay, they will depend on the transmission coefficients of the beam splitters. There could be some loss, some attenuation, so on and so forth. So K1 and K2 in general are complex constants. Okay, so this is what it is. Right. So basically we are the field. So this interferometer does not have any active element. So it does not have any element, any material or object with which the optical field, the beam, can interact, right? So all the components are passive, like beam splitters, mirrors, so on and so forth. Okay. So this is what it is. Right. Now we calculate the intensity. So this is the definition. This is how we define the intensity. So this is measured at the detector, right? So I of RT is simply V conjugate This is what it is. So all we have done is simply we have just taken the explicit form of V of RT, complex conjugated that one here, and multiplied that one by V of RT in terms of these two terms. Okay. So if one explicitly multiplies the terms in the brackets, we will get V star of R naught T minus T2 V of R naught minus T2 plus this is going to be the complex conjugate, the fourth term will be the complex conjugate of the third term. That's what it is. Now, this is nothing but the intensity of the field measured at R naught and time t minus t1. So the first term is the intensity at the space-time point R naught t minus t1. The second term is again the intensity measured at R naught and time t minus t2. So now you can see that the third term is nothing but the cross correlation function of the field at these two times, t minus t1 and t minus t2. And the fourth term is basically the complex conjugate R naught t minus t2. This is what it is. So we have written down the intensity at the detector in terms of the cross correlation function of the field at R naught and times t minus t1 and t minus t2. So the idea here is that by looking at the intensity of the field at the detector, so this is the intensity measured at the detector. So by measuring, by looking at the intensity of the field measured at a detector, we should be able to investigate the correlation between these two instants of time. So that's the this is the generic method of the second order coherence theory. So this is what we do whenever we wish to investigate temporal coherence in the second order coherence theory. So since we are only looking at the temporal effects, we will remove the spatial labels for simplicity. So we will simplify the notation. So basically we'll write this is the field at the detector, and the intensity can be written as so this is the general temporal interference law. So the intensity measurements at the detector yield the correlation function at the source. Okay. So by looking at the measurement of the intensity at the detector, we will be able to study or appreciate how the fields are correlated at the source, temporally correlated at the source. Now recall that K1 and K2 are complex numbers in general. Okay. So which means K1 star K2 can be written as we can write them in terms of their magnitude and phase, right? And this cross correlation function can be written as, this is as it is, but we can always multiply and divide now this factor, this is nothing but the degree of temporal coherence. In general, the complex degree of temporal coherence, to be more precise. So this is nothing but so now what we do is we are just going to so gamma is also complex in general. So you can always write this in terms of its magnitude times some phase, mod of gamma times e power I phi gamma. So now we can put everything into the expression here, and we get so cos of phi r plus phi k. So this is of the interferometer. Now this expression is something that is familiar to us. So this is what we have seen in the Young's double slit experiment too, except for the fact that in the most ideal case, people will always, we assume perfect coherence, so this mod gamma was set to unity, okay, and we ignored the time dependence in the arguments of the intensities. in the most elementary case, this would be simply mod k1 squared I1 plus mod k2 squared I2 plus all these factors without a time dependence time cos of phi. Okay, so this is the interference term. So when the argument of cos is +1, you get the bright fringes, and that's the constructive interference. When the argument of cos is -1, you get the dark fringes, and that's the destructive interference. Okay, and that's a very useful concept while investigating interferometers and studying interference, and that's called the visibility of the fringes, which by definition is I max minus I min times divided by I max plus I min. Of course, this also tells us that if there is no correlation between the fields at times t1 and t2, then mod of gamma goes to 0, because please recall that mod gamma always varies between 0 and 1. When mod gamma is 1, it means that the fields have perfect coherence, perfect correlation. When it is 0, there is no correlation. When this is 0, the interference term vanishes, which means we won't observe any interference at the detector. When this is 1, you will get perfect interference, and for any value between 0 and 1, the field is partially correlated, and that will get reflected in the contrast of the interference fringes. So
in the experiment of interference, it is visibility, that is what one calculates, right?
Yes. So basically, everything is, because in a moment this visibility can be related to mod gamma.
Yes.
So from the visibility, we pretty much get, or even of course formally we can also relate the intensity to mod gamma and everything. But it's the visibility, the contrast, that is going to really reveal to the experimentalist how good the correlation is. So this is I. So I max is basically.
My question is, why just taking this particular form of visibility? I could have taken I max by I mean or something like that.
So this particular form, when I max minus I min by I max plus I min, that really sort of gives us an expression where this visibility will be proportional to this mod gamma. So in a sense, and in the special case where, say, let us say these two are equal, the intensities of both the arms are equal, the visibility simply becomes equal to mod gamma. So this definition gives us a direct way to relate the visibility to the degree of coherence. So from this definition, I max is just sum of these two terms plus 2 k1 k2 times this term, and I min is mod k1 squared plus mod k2 squared minus 2 k1 k2 times whatever, because for I min cos is -1, for I max cos is +1. So okay, so this is how visibility is related to the degree of temporal coherence. Now let us consider a special case. If in this case, basically if the intensities in both arms of the interferometer are equal and all these factors, the so-called loss factors are mod k1 square and mod k2 square are equal, in that case so your visibility is so, and this tells us that in this case you can clearly see if mod gamma is 1, in which case which means that there is perfect correlation between the fields at times t1 and t2, then the visibility is 1. So visibility always varies between 0 and 1. So 1 corresponds to the best possible contrast in the interference pattern, and 0 corresponds to no interference at all. And any value for any value of the visibility between 0 and 1, the contrast will be reduced. The contrast of the interference fringes will be reduced depending on how small or how large the visibility is. And we know that the degree of temporal coherence varies between 0 and 1, the magnitude, the modulus. So if it is 1, V is 1, which means that perfect correlation corresponds to the best contrast, the highest visibility. And gamma, if mod gamma is 0, if there is no correlation, or if the field is incoherent, if the source produces an incoherent optical field, there won't be an interference. So which means the visibility is 0. And for partial coherence, that is for a value of mod gamma between 0 and 1, the visibility will also take that value between 0 and 1, in which case the contrast of the interference fringes will be reduced. Okay, so now next we'll talk about quantifying temporal coherence. So once again we'll just write down the result. Plus CC. CC stands for complex conjugate. Okay. Now, let us recall the generalized Wiener-Khinchin theorem that relates the cross correlation function to the cross spectral density. So this is the generalized Wiener-Khinchin theorem that relates the cross correlation function to the cross spectral density, and they form a Fourier transform pair. So this is the generalized Wiener-Khinchin theorem. So in general, it's not always easy to measure the correlation function. Of course, we have the setup. You can always build the setup, but it's not that it's always possible for any kind of spectrum or any kind of correlation. It will be easier to measure the correlation function. So we'll categorize the situations in which we can and we cannot measure the correlation function reasonably easily in the lab. So of course, the correlation function is related to the cross correlation function is related to the cross spectral density. So depending on the frequency correlations of the source, a source field can be divided into the following three categories. So case 1. So no correlation between different frequency components. So if there is no what does it tell us? Which means each spectral component of the field is independent of the other. There is no correlation between different spectral components. In that case, the cross spectral density is written this is the definition, the formal definition of cross spectral density. It takes this form. The presence of this delta function tells us that there is no correlation between omega 1 and omega 2, right? And of course, this is a stationary random process. We have seen this one earlier. And in this case, the correlation function will not depend on the origin of time. So it will only depend on the difference T2 minus T1. Okay? So in this case, intensity for a stationary random process, the intensity doesn't depend on time. So whatever be T1 and at whatever time you want to measure, it's just going to be the intensity at time t equals 0, and that's the same thing for I of t minus T2. This is essentially going to be this one, where tau is T2 minus T1, and gamma of tau by definition is this one, right? So which means the intensity at the detector I sub d, this subscript d stands for the detector, there should be intensity time. This is what it is. So in this case, the intensity will not depend on time, because for this particular kind of cross spectral density, the intensity is independent of time, and the intensity at a detector can be related to to gamma of tau, right. So, and one, of course, one can always calculate in this case the degree of spectral coherence.
So tau is basically the time difference, right?
That is true. Basically,
Minus
T2 that is determined by the difference in the path length of the.
It doesn't matter at what time the detection is being done.
Exactly. So that's what it is. Okay. So
Unless there is something in between.
yes.
That between the interferometer and the detector, if something extra is happening.
Oh yes. As long as the phase difference is only due to the difference in the path length, and as long as there is no correlation between the different frequency components, as long as we have this condition is satisfied, the intensity will not depend on time. So by measuring from the intensity or from the visibility, we should be able to investigate gamma, the temporal coherence, for this particular case. This is case 1. This is one of the extreme cases when there is no correlation between the different frequency components. Case 2. Perfect correlation between different Now, when the source has perfect correlation between its different frequency components or spectral components, the cross-spectral density is given by this expectation value goes away, and it's simply because of perfect correlation, there is nothing random, there is no averaging to be done. So the ensemble average of v tilde omega 1 and v times v tilde omega 2 is simply the product of v tilde omega 1 times v tilde conjugate of omega 1 times v tilde of omega 2. So what does it tell us? There is no randomness in the process. The frequencies are perfectly correlated.
There can also be the case where the frequencies are neither uncorrelated nor perfectly.
Yes, so that will be the next case, and these two cases will be the two limits.
Yeah.
So that will be the case of partial coherence, and that is what is the well-known Gaussian shell model source.
Yeah, so you can take basically some particular form of correlation.
Exactly. And depending on the parameters, the values of the parameters, the values of the parameters will determine how strongly or weakly the source is correlated spectrally. So we'll just come to that in a moment. Correlated. So
by looking at the field,
uh-huh.
Ultimately you'll have to do the detection, right?
Right.
Intensity or whatever. One should be able to figure out whether the field at different points are temporal points, are perfectly correlated or not correlated or partially correlated.
Yes. Yeah, that is true. That is true. Because once typically it's more natural to determine the spectral density, because even without building an interferometer, as you know, from the source you pass it to a spectrum analyzer and one can get the spectrum. So then the Fourier transform of that one gives us the correlation function in time. So that's why we always start with the cross spectral density and then try to determine the cross correlation function. So this cross correlation function is basically, and once again, so in this case, of course, the correlation function depends on both the time arguments t1 and t2. So this is not, this process, this case doesn't correspond to a stationary process. Okay.
Sir?
Yeah, please go ahead.
For this, any practical example you can give for case 2?
You mean for perfect correlation? Well, most of the beams are basically partially correlated, but then if you really want, the closest thing to case 2 is a pulse laser. So the pulse laser that you use in the lab. So if you look at the pulse structure in the intensity profile, is due to the fact that all the frequencies of its spectrum add up coherently. So a practical example for case 2 is the pulse laser. Yeah. So maybe 3:30, so 15 more minutes to go. So I of t is so this is how we formally calculate intensity, and the exact form depends on v of omega, v tilde of omega, the nature of the spectrum. And again, the intensity also in this case depends on time. Not stationary. So but in this case, once again, if you measure the intensity at the at a detector of the interferometer, complex conjugate, and once again depends explicitly on time. Now, case 3, which is the most realistic scenario, which is what we always encounter in labs. That is partial frequency components. An example, well-known example, is the Gaussian shell So we'll briefly mention. So we will mention what this source is, what this model is, but we won't be able to go into all the details because that would take us on a different trajectory altogether. But this is how the cross-spectral density looks like for a Gaussian shell model source. So the cross-spectral density is a product of two Gaussians, as you can see here. This capital omega is the frequency on which the spatial coherence width or the beam radius of the source depends. So please note that whenever a source produces an optical field, it produces in the form of a beam, okay, not in the form of an ideal harmonic wave. And omega c is the frequency that determines, or maybe I should write this one on the other side. The spatial coherence. Which describes how far apart points must be to have a high degree of correlation. To have a high degree of correlation. So this is the general form of the cross-spectral density of a Gaussian shell model source. Now, consider this limit omega c approaching 0. In this limit, it's simply this term becomes the delta function, right? In the limit omega c approaching 0, the second Gaussian becomes a delta function. Okay, so basically this is nothing but this is the first case that we consider, the case of no correlation between different frequency components. Now let us take the second case, omega c approaching infinity. So in that case, this becomes 1. The second exponent becomes 1 when omega c approaches infinity. So basically simply we have the first term, which is just this one, but this one can be written as a product of two exponents. So this is very similar to the second case, perfect correlation. So this is the Gaussian shell model source is the most general setting that corresponds to a partially coherent source, a source that produces a field that is partially coherent. And the case of perfect correlation and no correlation are just the limiting case forms of the Gaussian shell model source in the limit omega c approaching 0 and infinity respectively.
But how does one figure out that your cross spectral density, whether it is of this Gaussian form or not?
So one actually, I have a feeling that once the field is produced by a source, it should be passed through a spectrum analyzer, and then they look at the spectrum, the raw data, and then they try to do a fitting.
Yeah, but then you'll have to, because you are looking at two different points, right? Two different.
That is true, yes.
Yeah.
But so in the first case, when the spectrum is being analyzed, no interferometer is used directly. Yes, from the source you pass it through a spectrum analyzer,
Yeah.
and then look at what is the nature of correlation.
Then you can estimate that what will be this kind of
the functional form, what form what form
but
most.
Really, what happens? Generally, is it a good approximation to what happens in?
Yes, this is a well-studied model. So basically, this is a very good approximation to the source that we have in the lab, or the sources that are produced in the lab.
Oh, I see. So otherwise, this may happen that such such as cross-spectral density does not even exist.
No, this is probably this Gaussian shell model is one of the most used models. So yeah. So we'll stop here today, and we'll meet this Friday at 2:15, the same time, and we will quickly consider the special case of a stationary quasi-monochromatic field with Gaussian spectrum, and see how the coherence time and the bandwidth of the spectrum are defined, and then we'll move on to spatial coherence. So with the quasi-monochromatic field with Gaussian spectrum, we will wrap up our discussion on temporal coherence and then move on to spatial coherence. We'll briefly discuss spatial coherence, and then we will branch off to quantum optics, discuss correlations in quantum optics, bunching and anti-bunching effects. So any questions from the people attending online?
Questions, sir?
No, any question or no questions?
No questions.
Okay, thank you. We'll meet this Friday.